So actually sometimes even a delay of 5 nanosecond, a delay of 100 nanosecond is actually a bigger delay. It's even a bigger delay. Now let's say if you have interface with memory, you want fast data. Okay, you're receiving one data faster, but if you want to transfer millions of transactions and you are watching a video, you need higher bandwidth. If you look one frame, if you look at one video frame, okay, it's a one frame, but if you look at the data, one frame of data is actually maybe 1 MB or 2 MB of data.
Yes.
So actually there the delay matters. There the delay matters. So actually it depends on the user requirement that whether you want good resolution. If you want good resolution, you will go for a faster clock. If you want to increase the range, you will go for a, and resolution is not a problem, you will go for a slower clock. Okay. Okay, now one option is to use this terminal count. One option is to use terminal count. One option to increase the range. One option is to increase the range is to use different clock frequencies and use a multiplexer and a mode register. There is also one other option to increase the range. There is also one other option to increase the range. The use of cascaded counters. The use of cascaded counter. Now let's assume that if you have in the market there are two counters available. There is only one counter available. And your clock frequency is fixed. You cannot change the clock frequency. You have only a single clock frequency. You have a single clock frequency. Let's say the frequency is 1 GHz. And now you have a 16-bit counter. And now you have another 16-bit counter chip. Your two chips, clock is 1 GHz, and you want to model a delay of 9362145 nanosecond. Can you model it with a single counter? Can you model it with a single counter? Why?
It's greater than the maximum range.
Yes, it's the maximum. It's maximum in the range. And the maximum range of this is 65,535.
और उसका भी 65 है.
And it's 65,535. 35. So how we can increase the range? Use the counter in a cascaded fashion. Use the counter in a cascaded fashion. Now what's happening? Now if you look at now we have used these two counters in a cascaded fashion. Okay, now this clock is running at 1 GHz. It's 1 GHz. It's called as the, and now it has a top signal. When the top signal will be generated, we will reach the maximum value.
Yes, sir.
And this will be given to the clock of this counter. To the clock of this counter. Now what will happen? Now I will explain. Now if we have 1 GHz clock, so we have a faster clock. So what is the faster clock? Now this is your faster clock. Initially what will be the value of this count? I call it count 1. Count 1. So what will be the value of count 1? 0, then 1.
65,000.
When it reaches 65,005, 35. The top signal will be 1. Top will be 1. Initially top is 0. Now top will become 1 for 1 clock second. And then when it reaches the maximum value, it will wrap around. Then it will reset to 0.
Yes, sir.
The top signal will become 0. Now this is the input to the second counter. And now this is count 2. So now count 2 is now, this is count 1 and this is count 2. What will be the value of this count? 1. Again, when it reaches the maximum value, then again the top signal will be 1. What will be the value of this counter? 2.
Yes, sir. Nested loop जो है वो एक.
It's not nested loop. It's a hardware configuration.
Yes, sir.
Just think. Just think. Now let's assume if you have a stopwatch.
Yes, sir.
If you have a stopwatch, in a stopwatch, what's happening? There are 2 digits for the seconds. When it starts from 000 to 59, when it reaches 59, it's reset to 0,
Yes, sir.
and the minutes is then incremented by 1. So actually, so maybe this is a small, just like assume this is a second. When it reaches its maximum value, it will be right around. When it reaches 65,535, it will be right around to 0. The top signal will be 1. This signal is then given to what?
2 minutes.
Next counter.
Next counter. Next counter.
And next count value. Okay, now, so this type of counter, now there are 2 top signals. One is top 1 and one is top. And now what is the maximum resolution?
65,535 को स्क्वायर करें.
उसको इस तरह से करें, इसको इस तरह से स्क्वायर करें, इसको 32 minus 1. If you are cascading the counter, it is an n-bit counter, it is actually 2 n minus 1. So actually it should be 2 n minus 1. And if you cascade it 3 times, 2
Yes, sir.
3n minus 1. Okay. Now prescaler. A prescaler. Okay. This is the same, very simple. Prescaler clock. It divides the clock. It divides the clock. It divides the clock. It divides the clock. Increases the range and decreases the resolution. Now it's the same clock. It's the same clock. When the mode is 00, it will be clock. When the mode is 01, it will be clock divided by 2. When the mode is 10, clock divided by 4. When the mode is 3, clock divided by 8. So depending on the mode register, it will configure the.
Prescaler.
It will have different frequencies. Now we will do previous examples. Now we have a multiplexer and we have different clock. So in the prescaler, it will be determined by the mode register. Actually, if you remember in your digital logic design course, divide a clock by 2 is very easy. How you can divide it by 2?
Logical shift right.
No. Let's say you have flip-flop. You may have studied in the digital logic design course. So now let's assume you have a clock. It's a D flip-flop. The Q is the output. Q is the output. If you invert this, what is happening? Now it's your D flip-flop. It's your Q output. It's your clock. It's your clock. It's your clock. It's the rising. Let's assume this clock operates on the rising edge of the clock.
Yes, sir.
Okay, now initially we assume that the value of D is 0. The value of D is 0. We assume the value of D is 0. When the value of D is, let's say we assume that the value of Q is 0. When Q is 0, what will be the value of D?
1.
When Q is 0, the value of D will be 1. So the value of D will be 1. So Q is 0, D is 1. Okay. Now at the rising edge of the clock, what will happen at the rising edge of the clock? Q will be assigned the value of D.
Yes, sir.
Q is 0, D is 1. D is 1. So actually it will move from 0 to 1. Now the decision will be taken on the next clock cycle. When Q becomes 1, now you have an inverter. But now D will become 0. And the next rising edge. It will happen like this. Can you see Q? Q. If this clock period is 1 millisecond,
So this will be 2 nanoseconds.
so this is now
2 nanoseconds.
2 nanoseconds. Now it is clock by divided by 2. If we want to divide it by 4, what we can do? Use another flip flop.
Yes, sir. Cascaded.
We can use another flip-flop and flip-flop. This Q can be then input here and then. So this is clock by 2. Then it is clock by 4. And then again crystal head counter, then clock by
8.
By 8. So actually dividing a clock by 2 is easy to implement. You only need one flip-flop and one inverter. For divide by 4, you need 2 flip-flop and 2 inverter. Divide by 8, 3 flops and 3 inverter. Divide by 16, 4 flip-flops and 4 inverters. So if you look at the internal implementation, of this pre-scalar, maybe internally, and now there is some finite state machine that will be controlling all this. So this is a mode register, and this mode register will be configuring. So actually now if you look at here, now this is clock. Clock is input. So now you can use a multiplex. So now multiplex, you have no clock. Where is clock? Clock is here.
Yes, sir.
Then clock divided by 2. Clock divided by 2 is actually the output of the first flip-flop. And what clock divided by 4? Is the output of actually the second flip-flop. Clock. So 0, 1, 2. This is clock. Now let's assume that the clock frequency is 1 nanosecond. The clock frequency is 1 gigahertz. If it is 1 gigahertz, what will be the clock period? 1 nanosecond. Clock divided by 2. What will be the period?
2 nanoseconds.
2 nanosecond. Clock divided by 4.
4 nanoseconds.
4 nanosecond. And for the fourth, now you can have a mode register. In the for 4, you can just generate an event. So now it's a counter. 16-bit counter, any counter you can use. Now if you look at this structure, it is supporting clocks with multiple frequencies. That has a trade-off between different resolution and different ranges. And it's not only supporting clock with different frequencies, but it's also supporting in events. So it's a multi-purpose counter. And being as a hardware designer, you can design a multi-purpose counter, a timer structure that can not only count the number of clocks events, but with different flavors. And different flavors include different ranges and different resolutions. And depending on the requirement of the user in terms of ranges and in terms of resolution, you can configure it through the mode register. This mode register can be controlled by a microcontroller, a microprocessor. Okay? And then you can also configure it as an event timer in which you can count the number of events. Now, reaction timer. What's the reaction timer? It measures the time between turning light on and user presses button. It's the resolution. Resolution is 6 multiplied by 8.3. So it's a 16-bit timer. Let's say we have 16-bit timer. Clock period is 83.33 nanosecond. Counter increments every 6 clock cycles. The clock period is and counter increments every 6 clock cycles. So what is the minimum resolution? 6 multiplied by clock period is 0.5 microsecond. What's the maximum range? 65,535 because it's a 16-bit counter. Multiplied by 0.5 then it is 32.3 millisecond. Can anybody elucidate from this slide? Okay, just look at this slide and can you explain what's the reaction counter? It's all the concepts is similar to the counter, but there is one difference between the reaction counter and other counter. आपने कभी वो गेम शो देखा है या नहीं देखा? सारे लोग बैठे होते हैं वो सवाल बजर वाले एंड व्हेन अ यूजर प्रेसेस अ बटन जो सबसे पहले बजर बजाता है तो वही कंसेप्ट वही है but it's the hardware structure, वही चीज़ है. It calculates the delay. जो पहले वो करते हैं, आपने देखा होगा कि जो वो टाइमर नहीं होता है ना, चल रहा होता है, जैसे वो प्रेस करते हैं वो स्टॉप हो जाता है. ठीक है. सो इट्स एन एग्जांपल ऑफ रिएक्शन काउंटर. सारी चीज़ें वही है, जो कॉन्सेप्ट वही है, बस सिर्फ जो है ना वो कॉन्फ़िगर इट इन डिफरेंट. वॉच डॉट टाइम. व्हाट्स अ वॉच डॉट टाइम? What's a watchdog timer? Can anybody elaborate? When what's the use of a watchdog timer?
It counts the number of instructions executed. and
No,
cycles.
no. If you look at this, must reset timer every X time units, else timer generate a signal. There is a specific use of it. You may have remembered. Now let's assume sometimes you insert a card into your ATM machine, okay? ATM machine, and sometimes it pushes back the card. When it's hanged, it pushes back the card. Why? It's because of the watchdog timer. So actually, it's actually used in a scenario. Actually, when you insert your card, and the user does not know how to operate the system. If he presses some button and the system is not expecting some events, actually whenever you insert some cards, so the system is expecting some input from you. The system is expecting some events from you. Now there are two scenarios. When the user insert his card and the user does not press anything for 2 or 3 minutes, what will happen? Timer. So actually there is a watchdog timer inside. There is a watchdog timer. It's expecting some input and it's reset the system after each and every time. So actually it's used to avoid any unanticipated events, unpredictable events. Let's assume user presses something and it's input some data and it just is pressing enter 5 times. The system is not expecting that event from the user. So in this case, a watchdog timer, and a watchdog timer is actually a robust system, a self-safe, a fail-safe mechanism. And actually it's installed at a place like, let's say if in ATM, and let's assume actually whenever you want to design some kind of system, you should anticipate all kind of possibilities. Now let's assume if we say that A divided by B, I want to write this program A divided by B. A divided by B. Now if you are a good programmer, what should you do?
B should not be equal to Z.
B should not be equal to Z. So if you are taking this input from the user, so then there should be a check. If B is equal to 0, then print divide by 0 error. So actually you should take care of all the possible error scenarios. You should take care of all the possible error scenarios. So watchdog timer is used in this scenario. It's commonly used to detect failures or self-reset. So sometimes it's also called as timeout events. So actually when the system is expecting some input from you and the user does not give that input for some specified interval time, it means that okay, now it is something wrong has happened, so it will generate an event and then it will move to a code, maybe start some system, it will jump to a code system. Let's assume if you insert your ATM card and there is some reset subroutine, it will jump on that reset subroutine and then that subroutine will say okay, if somebody has pushed some like ATM card, we should give back the card. This is another scenario. Now let's assume you input an ATM card and the system gives you the ATM card out back and the user does not collect it for 2 minutes. What should the system do? Capture the card by itself. The same is true for the cash. So there is a lot of mechanisms. How it will behave, it all depends on the user requirement, on the bank requirement. Let's assume one bank may have one policy, another bank may have other policy. So actually the user actually is if you look from the development perspective, who is the user? Actually the bank is the user. and he will give all these specifications to the programmer. Okay, design my ATM like this. So it will cover for all the unanticipated events, and in case of unpredictable events, there will be a watchdog timer, and a watchdog timer which provides a fail-safe mechanism. Okay, so there is also some coding. Please go through the book and go into the details of how it works and how, like, while transition is product is button press. So it's the same scenario setup we discussed. Okay, pulse width modulator. So it's also called as PWM. PWM. It generates pulses with specific high and low time. It generates pulses with specific high and low time. It will also called as a duty cycle. What is a duty? What is duty cycle? B.
जितने टाइम के लिए वो ऑन रहता है.
Yes, the percentage of time a pulse is high and compared to the low time. So actually, what is duty cycle? So duty cycle is equal to high time divided by high time plus low time. I'll explain this with an example. If you look at this PWM signal, it means that now the first PWM signal is high for 2 clock cycles and low for 6 clock cycles. Clock cycle 1, clock cycle 2, and it's low for 1, 2, 3, 4, 5, 6. So what's the high time? 2 cycles. What is the high time? Is 2 plus 6. And if you say 2 divided by 8, it is actually
25%.
25. If you look at the second signal, 1, 2, 3, 4, for 4 clock cycles it is high, and for 4 clock cycles it is
50%.
low. So 4 divided by 4 plus 4, 4 divided by 4 plus 4, and it is actually 50%. And if you look at the last one, for 6 clock cycles it is high, and for 2 clock cycles it is low. So actually the duty cycle is now
6 by 8.
75. Okay, now what is the purpose? What is the purpose of this pulse width modulator? The common use of it is to control the average voltage to an electric device. And it is simple like DC to DC converter or DC to analog converter. And it is also used for DC motor and dimmer lights. DC motor and dimmer lights. Okay? Another use is to encode commands receiver, and I will explain this with an example in the next slide. What is the advantage of the PWM signal? Okay. Now you understood with this that if it is a PWM with 25% duty cycle, it's a PWM with 50% duty cycle, and it's a PWM with 75%. So the common use is to control the average voltage to electric devices. Okay, one example is to control the DC motor speed. To control the DC motor. I will explain this in my next slide. How we can control the DC motor speed. Now, if you look at the DC motor, now this is the DC motor. The DC motor. The input to DC motor is 5 volt. Now there is a transistor here, and this signal, this is a PWM signal. That is generated from where?
Processor.
From the microprocessor. That signal is generated from the microprocessor. When the signal is generated from the microprocessor, so if you look at here, so if the input voltage is 0, okay, so what is the percentage of maximum voltage applied? 0, 50, 75 and 100. Okay, in this case, what is the PWM signal?
100%.
100% duty cycle, it will always be high. With 75%,
75% duty cycle होगा.
it's 75%. In the previous example, it was high for 6 clock cycles and low for 2 clock cycles. With 50% duty cycle, it was high for 4 clock cycles and low for 4 clock cycles. Okay, now we can control the RPM. What is RPM?
Speed.
Revolution per minute.
Speed is.
So the speed of the motor, this is controller. So if we have a very high duty cycle, the motor will run at a highest speed.
Highest.
And if we decrease the duty cycle, the motor will run at the lower speed. What's the advantage of this mechanism? The advantage of this mechanism is that you can easily generate this PWM signal from the microprocessor. And it's a digital signal or an analog signal?
Digital.
Digital. PWM. I'm not saying it's a PWM. If you look at the first signal, it's a PWM signal. It's a signal. It's a digital signal. It's a 1-bit signal. It's actually a 1-bit signal. In the PWMO, in the first case it's 25% duty cycle. In the second case it is 50%. In the last case it is 75%. So it is easy to generate a PWM signal from a microprocessor using only 1 bit. So you can connect it. You can connect this pin with your microcontroller. You can connect this pin with a microcontroller. Okay. How you can generate this PWM signal? You have a clock, then you have a clock divider, then you have a counter, then you have an 8-bit comparator, and then you can generate this PWM signal. How? I will explain this within examples. Now let's assume if within the microprocessor, if you have counter in the microprocessor, okay, one counter in the microprocessor, and let's assume this counter is 8-bit counter. This counter is a 8-bit counter. Okay, what will be the minimum count and what will be the maximum count?
0 to 55.
From 0 to? It will count from 0 to 55. Okay, now initially what you will do? You will set the signal as high. You will set the signal as high. So set the signal, let's assume it's P1.0. P1.0 is now high. If you want a duty cycle of 25%, when should you make it low? When it reaches 64. Understand? Okay, if you divide this 256 by 4, it is 64.
Yes, sir.
So it will be high. From 0 to 63, it will be high. And from 64 to 255, it will be low. What is now the duty cycle? 25%. Now if you want to generate a duty cycle of 50%,
तो 0 से 128 तक
from 0 to 127 it will be high, from 128 to 255 it will be low. Now if you want to generate a duty cycle of 75%,
0 से लेकर 190
192. From high, from 0 to 192 it will be high,
और 192 से
from 192 to, so for 255 it will be
low.
So now it's actually easy to generate. Now this is the control flow of this. This is the control flow of this duty cycle. And actually, now this is one method. This is one method. This is also another method. कैसे कर सकते हैं?
ये तो काउंटर से टाइमर से भी
You
कर सकते हैं.
can write a simple assembly language program.
टाइमर से भी कर सकते हैं.
OAS can do that.
Serial data within 1110.
No, you can write a simple assembly language program for that.
टाइमर्स में
Timers. You can initialize a counter, move. ये है ना? Move R0 hash count
equals 0 2h 25h
255. ठीक है?
Yes, sir.
Count 0. Okay, now we say set P1.0. Let's assume we have set this signal. Initially it's 1. Set P1.0. Decrement R0.
Yes,
Compare R0 with Z64. We are generating what? Duty cycle.
Yes, sir. Yes.
66, 25%. Branch.
Equal.
If it is less than B and T, if it is less than 64, it should jump again Okay, again decrement. And if it's when it comes out of again, then we should clear P1.0.
सिंपल एक डिले का फंक्शन बना देते
Yes,
हैं
it is a delay का function. A lot of possibilities are there. This is one of the possibility. Then you compare decrement R0, compare R0 with 0. Let's say when it reaches 0, then you just move on start. You can have a small assembly language program. Now this is just like an overview and how you can write a small assembly language. You can also write a small assembly language program for that. You can also use a built-in counter within the microcontroller or microprocessor, and the built-in counter will serve that purpose for you. So actually, this is the way that we can now generate a PWM signal. And there are also some microcontrollers, and in that microcontroller there is also an internal timers,
टाइमर्स
and you can then configure that timers. You say, okay, now maybe there is one timer within a microcontroller, and you say, okay, I want to configure this timer as a clock counter. I want to configure this timer as an event counter. I want to configure this timer as a PWM signal with 25% duty cycles. There is a lot of configuration registered within the microcontroller, and you can configure these timers. These are dedicated timers. LCD controller. G. LCD controller. G. जो